let me thank the organizers for the invitation. I was unfortunately unable to join because basically I'm in Greece, and it's a 9-hour, I think, time difference, and it's actually Friday night here, so it's a little hard to give a talk at this time of the day, but I'll do my best. So what I wanted to tell you about is Twistor amplitudes with a bit of a touch of celestial holography. This is based mostly on this recent paper, but also some work in progress with some people at Harvard. By the way, how much time do I have?
30 minutes for your talk and then 15 minutes discussion. I'll tell you 5 minutes before we end.
So you mean 30? 30?
30, yes.
Okay, thank you. All right, great. So first, let me motivate Twistor amplitudes. Well, for some of you, there is not really much motivation needed, but let me just remind you that historically, Twistor space was provided as a compact way of constructing nonlinear solutions to the self-dual wave equations. And there's a delightful paper by Penrose on this idea that essentially, because self-dual equations are in a sense linear, it provides a path forward towards quantum gravity because it's an integrable system. So you can read more about this in Penrose nonlinear graviton paper. More recently, as is mostly familiar, Twistor string provided a reformulation of gauge theory scattering amplitudes, in particular in Twistor string theory in Twistor space. And this reformulation exhibits novel features such as conformal symmetry and dual conformal symmetry, and again, it led to a path forward towards integrability properties of supergeometers. So integrability is one of the key words in this story, and actually the topic I'm going to cover, which is mostly related to the black hole classical solutions, is also one other aspect of integrability. So let me just, without, of course, I failed to give the proper reference here because there's the body of work is really large. But there is a three-way connection between Twistor theory, scattering amplitudes, and classical GR solutions. As I just mentioned, there's a connection between, by the work of Witten, also by the work of Penrose, and most recently a connection between scattering amplitudes and classical solutions in general relativity, as has been established throughout this conference. Okay, so one thing that's very nice about Twistor variables is that they provide an explicit realization of a certain infinite dimensional algebra, which was found originally in this paper and then reformulated as what is known as the W infinity algebra that applies for massless self-dual fields, and in particular for three-level scattering amplitudes. So the idea basically, in order to write down this algebra, I need to go through a reformulation of the S matrix in asymptotically flat spacetimes, which has the name of celestial holography. And it's basically the idea that if you have massless particles reaching null infinity, they define an operator insertion in the celestial sphere. And these operator insertions, we can obtain them from boost eigenstates rather than momentum eigenstates. And so they transform nicely under conformal transformations, which is the Lorentz group in Minkowski spacetime. Okay, so we have our operator insertions here in the celestial sphere. The important point is that they obtain as boost eigenstates. So the map from the usual amplitude to the conformal correlation function is given by this Menin transform. The insertion of the operator at the celestial sphere is given by this parametrization, set and set bar being the coordinates. And once we do that chain basis, what we gain almost for free is null symmetries. One of them is an extension of U1. In the case of gauge theory, we have Kavli symmetries, Virgo symmetries, and most recently we have this new symmetry, which is W. So if I take my amplitude in this parameterization, the action of this generator is given by this expansion, which is basically of conformal descendants. Now, what's the takeaway from this algebra is the following. So we have an infinite number of generators. The 3/2 generator is associated to translations, or the BMS generation. The spin 2 generator is associated to rotations or super rotations. Let me just call them SL2C. And so there is an infinite extension of those. Okay, so it's an infinite extension of Poincaré algebra. I will cover more of this later. It might or may not be a little abstract to you because you have to take all these derivatives and so on. But the important point is that even though this algebra seems quite complicated, it can be reformulated in Twistor space. I'll just mention that in a second. Let me just give you very quickly what are the structure constants of this algebra. They depend on this mode expansion that I just showed you, and they are in a sense kinematic because they are determined from kinematic invariance in the scattering amplitudes. Okay, so there is some funny structure constants. If you do the same for gauge theory rather than gravity, you find something that's very similar, except that now you have color instead of kinematic. So there's an avatar of color kinematic replacement. Okay. Okay. So if that was a little abstract, then I hope that this other formulation makes it clear. The idea is that we can introduce another chain of basis, which is the Twistor transform. This is very much the Twistor transform that was introduced in Witten's paper, except for a slight difference, which is that we have to quotient the transform by a set 2. And this set 2, what it does is that in Twistor space is really most easily understood as a 2,2 signature space. And in 2,2 dimensions, there is no notion of energy. And so what you understand by future is the same as what you understand by past, up to some continuous Lorentz transformation. And so you have to quotient by that transformation. Okay. So that is just the notion that in and out are supposed to be identified in 2,2 signature. And now the reason that we're going 2,2 is because simply I can refer you to Witten's paper. It's easier to do and manipulate the scattering amplitudes in 2,2 and then to analytically continue. Okay, so 2,2 space was studied in this paper with some of my collaborators and also by Monteiro and Donald and the group in this nice paper. And so we want to now understand, for instance, the action of this W algebra, and it's actually very simple because if I act with my now I have my scattering amplitude, my usual scattering amplitude in terms of lambda and lambda tilde. I Twistor transform, and then what I get is that the action of this W algebra is now simply a Poisson bracket. Okay, so that's very simple. The Poisson structure is almost trivial, and you can essentially transform your Twistor function from a reference function to a new function. Okay, so for instance, now we can make a very precise example is W3/2, which I show you. It's the second element of this family and is associated to translation. So let's see how that comes about. You can check because W3/2 is actually just a single component sorry, I forgot to mention. So the Twistor space is given in terms of lambda and mu tilde. So that's an important point. What is doing this transform is essentially a Fourier transform in lambda tilde, and now my Twistor space is just lambda mu tilde. Okay. So in these variables, mu is just a simple power of mu sorry, W3 is just a simple power of mu, which is a derivative in mu under this Poisson bracket. Okay. And that makes perfect sense because we know that momentum in lambda and lambda tilde variables is just this. And then because we're Fourier transforming, we are essentially getting a derivative on mu. Okay. So Twistor space has many features. The momentum is a differential operator, but so is the conformal transformations, which are not differential operators in general. Okay. Or they are quadratic differential operators. Okay, so it makes certain symmetries more explicit. Okay, so there's recently been a body of work that relates the Twistor functions, which I refer to Twistor amplitudes, and the classical double copy. And the idea is that the origin of this double copy may be explained by these functions on Twistor space. So to see how that comes about, we need to first introduce some functions which are essentially carrying the gauge-independent information, and those are curvatures. So we understand, for instance, what's the Weyl curvature of certain solutions. And the spirit of the classical double copy is to relate this Weyl curvature to a strength, to a field strength. Okay, and so both of these expressions, both the Weyl curvature and the field strength, have the so-called Penrose transform relation to a Twistor function. Okay, so essentially what I do is I take my lambda variables and I do a contour integral of them, where the integral is given by this Twistor function, and what I get is a solution of the self-dual equations, which is what Penrose constructed, which is precisely this Weyl tensor, or the field strength, or the scalar or the scalar field in the case of spin theory. So I can do all these Penrose transforms. They exist in various dimensions, and they exist for all helicities. What they do is that they construct these functions of the space-time for you. Okay, and so I'm not gonna discuss it in extension, but very roughly speaking, you can see that double copy applies already at the level of the Twistor functions. Okay, and so the classical double copy, which is a relation between the space-time functions, essentially is a consequence of this relation, which is a relation between scattering amplitudes, just in the Twistor basis. So the example, which is the simplest case, arguably, is the Kerr solution, which can be obtained, or we understood a couple years ago that it could be related to scattering amplitudes for particles of infinite spin. And even though that was sort of clear because one can compute observables, it was not manifestly obvious how to relate that to a classical solution. No, in particular, how to relate that to the Kerr solution itself. And a way to do it is well, we write the Kerr solution in momentum space as usual. You can add node charge, you can add spin, right? So it's actually the Kerr tap NAT solution. It's a 3-point amplitude for a massive particle emitting a graviton. And it turns out that, well, this corresponds to self-dual and anti-self-dual pieces of a classical space-time where the self-dual or anti-self-dual is given by the helicity of the graviton, okay? And we know that these solutions exist actually in 2,2 because in 3,1 you don't have self-dual solutions because they are necessarily complex because the self-dual condition is a complex equation. And so in 2,2 you really have this sort of self-dual gravitons, as Penrose called them. So this decomposition of self-dual and anti-self-dual really makes sense in this signature. Well, this is just a word about the double copy. So in order to obtain a classical solution out of this 3-point amplitude, what we do is we Penrose transform, right? Sorry, we do a Twistor transform, which is Fourier transform in lambda tilde, and we get this function. The important point is that this function depends on x through something that's called the incidence relation, but it's shifted to x plus a when you have a spin. Okay, so that is one of the main features of the Kerr solution, that in the self-dual case, it can be obtained as a shift of the spinless solution. Okay. And so you look at this Twistor function, you can decompose it. It has some poles. You can it has a quadratic form, so you can compute its roots. These roots of these poles of the Twistor amplitude happen to have a physical meaning. In fact, Penrose noticed that these are nothing but principal null directions in the spinor form, essentially because they are agent vectors of the null agent vector of your strength. Sorry, your field strength, right? So here, the Weyl tensor given by this equation has a null agent vector given by the poles of this Twistor function, and so that's what is called a principal null direction. Because you have two, we say that this solution is type D, and that's exactly what you expect for Kerr. And in fact, you can just see that if you integrate the Penrose transform, you get this nice form, which is exactly the double copy, the classical double copy formula for Kerr. Okay. Okay. So that's all I wanted to say about twistors. And now I'm gonna slightly mention some work in progress that we have been doing with some people at Harvard. And it's mostly related to the previous discussion, except that the idea now is to understand the black hole metric from a two-dimensional perspective. Because of this idea of celestial holography, we know that the scattering amplitudes can be represented as correlation functions on the celestial sphere. And so given that there's a relation between the classical solutions and the scattering amplitudes, is natural to think that there is a two-dimensional dual of this classical solution. And in fact, that's exactly what I'm gonna show very briefly. The idea is that we take this Weyl tensor with the field strength tensor in Young-Mills, or the Weyl tensor in gravity, and we can expand it in terms of something called conformal primary wave functions. So these are just wave functions. They are functions of position, just to make it clear here, and these operators. And these operators, the important thing is that they are operators in the celestial sphere. So they depend on this set and set bar coordinates. Okay. The conformal primary wave functions depend on x. It's a very simple formula. And the idea is that I integrate over my conformal weight in this imaginary line, and I integrate over my celestial sphere. Okay. So I'm integrating my operators over the celestial sphere, but I'm integrating the weights of the operator in this imaginary line, which is called the principal series. Okay, so after you expand your Weyl tensor in this way, the statement is that the expectation value of this operator can be computed from 2D CFT state. Okay, so it's a correlation function in the two-dimensional field theory. And moreover, this expectation value transforms under the W algebra. Okay, that sort of follows from what I showed a couple of slides ago, which is that this algebra acts on this basis. So you can think of, instead of the scattering amplitude, as just having one single operator here, O delta. Okay, so we write the Weyl tensor in this basis, and this basis transforms under W, so in particular it transforms under translations. as I just showed. So translations are just the second generator of this W algebra. So you can get care again by acting with this generator, with this W generator. Okay, and the result, I'm not going to exactly explain the state, but the result, let me just summarize it, is simply this function. Now, if we plug back this function into our expansion here, what we get is this integral, and essentially this integral over this weight of the operator just reduces to so-called Mellin-Barnes representation, and it's just given by this function, which is exactly the Twistor function. Okay, so to summarize, what we did was to reproduce the Twistor representation of the Kerr black hole, starting from an expectation value. Starting from this expectation value. How much time do I have? 10 minutes? Yeah.
10 minutes, exactly.
Okay. So given that I have nothing else prepared, I will very briefly explain to you how to construct this state, just with pictures. And the idea is very simple. The idea is that you have your space-time. Down here you have your celestial sphere in coordinates z and z bar. And if we want to understand a black hole state, let me just make it a little bigger. If we want to understand a black hole state, one way to arrive at the black hole state is by introducing Wilson lines. Okay, so suppose I have a couple of Wilson lines. We know that Wilson lines, if they are massive, they start from past infinity and they go to future infinity. They can interact through some graviton exchange. And the important point is that each Wilson line can be associated to an operator in the celestial sphere, because I can essentially foliate my Minkowski space-time with slices, and so each Wilson line defines an insertion. Okay, and then essentially I can propagate this insertion into my celestial sphere. So this is how I map a Wilson line to a celestial sphere. Now, why is it that black holes themselves are described by Wilson lines? There are many ways to see this. Many ways, since a long time ago, we know that the eikonal approximation actually corresponds to classical expectation values of Wilson lines. So we take a 2-point function of a Wilson line here, and the other Wilson line is separated by some distance a. This 2-point function actually computes what's called the eikonal phase if the Wilson lines have no recoil. Okay, if they are straight lines. If the Wilson lines are slightly bended, actually what you get is a so-called Faddeev-Coolidge dressing, which I'm not going to write. But so many infrared effects and eikonal effects are actually captured by Wilson lines. Also, Reggie limit is completely captured by Wilson lines. So that gives you a good idea of why black hole state should be dual to Wilson lines. And very explicitly, we can compute. Sorry, let me just mention how much time I have. Oh, I still have a lot of time. Let me just mention that the important point about the state is that it's a charge under VMS. So why is that important? Because BMS is an extension of the translation group. So you can act on these Wilson lines with a translation generator, right? So if the Wilson lines are charged under translation, essentially what I can do is I can act with my generator. Here, the translation is W3/2. And what I can do is I can translate this Wilson line into this sort of complexified version of Minkowski. And as we know, or it's more or less familiar to some of you, that the Kerr solution can be actually obtained by a complex translation that's called the Newman-Janis shift. Okay, so that's why it's important that the lines themselves are charged under translation. Okay, and if you want to write the state, it's actually very simple. From the Wilson line formula, you just take the exponential of your Wilson line, your gravitational Wilson line, and if you want a soft-wall field, you just contract it with your metric and you evaluate on your position, and the translation is just a translation in the Wilson line. Okay, so in a sense, this is the dual the black hole state. Okay, so it's 5 minutes now, and I don't have more to say, but of course I can use that time for questions. So please let me just stop here, and any questions I'll be happy to answer.
Thank you, Alfredo, for your nice talk. Let's see if there are questions, both on Zoom or in the hall. Donald, please.
Hi, Alfredo. Yeah.
Hi.
So you've got all these BMS generators in 2-2 signature. Can you use those to act on observables and figure out the action of BMS on some observables, and then analytically continue them back?
Yeah, of course. As you pointed out in your paper with Uri and Yutin, I think. Yeah, one of the actions of the BMS is a super translation. So actually, a single translation would shift you from Schwarzschild or Tauvenat solution to Kerr-Tauvenat, and those translations happen to be complex super translations in 3,1, but they are actually real in 2,2.
Yeah, but you can do super rotations and everything else, right?
Yeah, exactly. So actually, this W1 plus infinity algebra is intrinsically 2,2 because it's a chiral algebra. So it acts only on the self-dual part of the field. Yeah, and that includes super translations and super rotations and other stuff that we're currently looking into.
Yeah, I guess I'm thinking that you could do this beyond 3 points, so 4-point things, stuff that's actually involves black hole scattering or physical processes like that. Would there be any problems with computations like that, do you know?
I'm gonna say no, but that would be irresponsible because
Yeah, great.
Yeah.
Yes, please.
Hi, Alfredo, it's Lionel. Thanks for lots of stimulating ideas there. But I was just a bit curious about Wilson lines in the gravity context. So I usually think of Wilson line as something in the Yang-Mills context. Is that so? How does one think about the gravity Wilson line in this context?
Right. So I guess Chris has done a big body of work on this. I think there was an objection at some point because these were not really gauge invariant, or they have some gauge transformation properties. I mean, the main objection was that Wilson lines were really coordinate sensitive. But that's perfectly fine for this picture, because what you really need is the Wilson line to be charged under super translations, and in a sense that's the defining property. If you have something that's charged under super translations, what it does for you is it takes care of infrared divergences, and it has this coherent state structure. So this is exactly the coherent state that you would get if you scatter a free particle and it exponentiates with soft radiation. So there are many ways to argue that these things are there in gravity just because you have infrared long distance force.
Yeah, I mean, I think I looked at that. Yeah, so those are essentially the action of a geodesic, of course, something is what those are. At least that was my memory. Is that right? Oh, sorry. Yeah. Oh, was I not speaking to the microphone? So Chris, Wilson lines were essentially sort of the action of a geodesic, and so here, then you're thinking about the action of the geodesic of the black hole, of course, that follows. So that's
yeah.
And then you were suggesting that those intersect the celestial sphere, whereas I was finding it difficult to see how they might do that. So were you trying to realize them as insertions on the celestial sphere?
Yeah, I'm not really going to comment on that because I will have to write down explicit formulas that I'm still cracking my head with. But I mean, there's a very natural way of doing it. But the idea is roughly that we believe that every state in the bulk has a 2D holographic dual. And so not only massive particles have a holographic dual, which it's very easy to derive. Massless particles have a holographic dual because they pierce the celestial sphere. But any sort of massive particle, Wilson line, black hole state, we believe that it has a holographic dual. So it should come to no surprise that these particular ones do have one.
Oh, well, sounds. I look forward to it. Cheers. Thank you.
Yeah.
Thank you. Other questions? Yeah, there's one.
Hi, Alfredo. Thank you for the talk. I have a question about these higher order generators in the W1 plus infinity algebra. Do they have like a more conventional?
Sorry, who is this? Just to.
Oh, this is Callum Jones.
Oh, thank you. Okay. Hi.
Hi. Do these higher order generators have a more conventional interpretation in terms of subleading terms in the soft graviton expansion?
Good. Yeah, so good. So we have this family of generators. I was a little quick to mention that the generators themselves correspond to plus or negative helicity gravitons. And so, well, for W, they are plus helicity, but there's W bar, which is minus. And so essentially what you have is expansion, the soft expansion of these operators, which are gravitons, and the sublean orders are precisely these generators. Yeah, so the lean order is the super translation one, and the sublean order is the super rotation one, and then we just keep going your soft expansion. And that's how you define these generators. Yeah.
Is there something that makes these, usually the terms beyond sort of some order become non-universal? Is there some reason why?
Right. So yeah, so they are non-universal. As far as I understand, people have been looking at effective EFT operators 3 level, and they have found that there is some correction to W to these structure constants, which is a little surprising to me because from Penrose's approach, the canonical construction of W is very rigid. And we know that it has corrections related to quantum deformations of the algorithm. Well, at least I haven't heard of classical corrections to W. So that's still some confusing point to me. I agree that the sublean orders are not universal, but also this is not exactly the full sublean order, but a projection which is obtained by taking certain descendants. And so there's some part of the sublean orders which may be universal. So the answer is we don't know, but that's what I suspect.
Thanks.
Maybe I can also ask a question. So this algebra is only for the plus helicity states, right? Still. So do you understand it also for mixed, so plus and minus?
No. So we don't really understand. Not even the simplest soft theorem, really, I would say, which is the sublean soft theorem. these commutators are precisely related to commutation of two subleading gravitons. Whether you take one or the other first, that makes a different result. And so that ambiguity, if you have different helicities, is present, and so we don't understand, or there's no unique prescription of coming up with a particular algebra.
Thanks. Lionel has a comment.
Sorry, sorry, it's Lionel again. I just wanted to refer to the work of, well, I guess in our W Infinity paper we had some comments on the mixed cases as well. You can, sorry, I need to speak directly into it. I'm sorry. Yeah, you can do, but I think actually that was developed further by Tim Adamo and Atul in their subsequent paper, where they really studied, and Eduardo Casali, I think, as well. So they studied the interaction of, I mean, so the W infinity and the tilde W infinity do mess each other up if you think about them semi-classically, but on the world sheet they decouple again, and you can understand them acting at the level of vertex operators, but they do have higher order poles between them. So thinking that they're no longer really realized as an algebra. But somehow in the formula they decouple, and you can see effects of soft theorems in that language. But yes, I'd refer you to the Adamo, Casali, Sharma paper. I think there's also Way. I can't remember who else was on the paper.
Thanks. Okay.
I look at that paper, and I will look even further now. Yeah, thank you.
Yeah, Donald.
Hi, hi, Alfredo. Just looking at your slide there, you have a kinematic algebra. Has this anything to do with these area-preserving diffeomorphisms in the self-dual theory?
Right. I believe these are the same. Just rewritten in a different basis. Yeah, essentially this kinematic algebra, it's basically controlled from 3-point functions. So it's essentially the collinear singularities that determine these commutators, or at least that's one way of saying it. And so even though we have some mode expansions, I believe it's roughly the same as, yeah. Yeah, sorry, did I answer your question?
Yeah, absolutely. Yeah.
Okay, maybe there's a question from Zoom land. I can't see everybody now. Doesn't seem to be the case, also not in the lecture hall. So let's thank Alfredo once more for a very nice talk.
Hey, thank you. Thank you. It was nice seeing you in Zoom, and I hope we can reconnect. I really have to go now because it's Friday night, and otherwise they're gonna kick me out of the room. So I'll hope to see you soon in person, hopefully.
Bye.
Bye bye.
Bye. Happy Easter.